So hello everyone. This is lecture 18 for the solid state physics, in which we were studying the lattice vibrations. And in the last lecture, I have given you these questions to solve. I hope you tried. Well, there was some mistakes in the questions. Here it was pi by 2a, not pi by a. And in this it was m tends to 0, m tends to infinity, capital M, small m. Okay, so let me give you the solution. First, the question was that atoms of mass m is at rest in the acoustical branch at this point. Okay, so we need to prove this. So how we can just say this? Here we need to prove that at this point the small m mass is at rest, and at this point capital M mass is at rest. Okay, and this is for the acoustical and this is for the optical branch. So acoustical branch small m is at rest, and for optical branch capital M is at rest. So how we can prove this? Just we need to take these equations. We already know from where these came. So first take the second one equation, and here we will solve for the acoustical branch. So omega negative at pi by 2a will be, at pi by 2a omega negative will be root 2 beta by capital M. So we just substitute here, and at k equal to pi by 2a this will term will 0, and at omega we will write omega negative, and just substitute this value root 2 beta by M. You will get this expression, and from this expression we can see that this term can't be 0, because m by m can't be 1. If this becomes 1 means we are dealing with the monoatomic, not diatomic. Means both mass should be different, and these mass, if these mass are different, then this term can never be 0. So this should be 0. And what is a here? A is nothing but the amplitude of small m mass. So we can prove that if a is equal to 0 means the maximum amplitude, so m is not oscillating. Okay, so it is at rest. Now similarly for the second one, we will use this first equation, and just substitute here pi by 2a, and here take for the optical branch, so we will take omega positive, and omega positive at this point is root 2 beta by small m. So just substitute, this term will turn out to be 0 because of cos 90 equal to 0. Now we again get this type of situation, this can't be 0, so b should be 0, and b is nothing but amplitude of capital M mass. So at pi by 2a for the optical branch the capital M mass will be at rest. Okay, so I hope it is clear to you. Let's just move to the next one. Now this was the question: discuss the behavior of acoustical and optical branch when M is decreasing and decreasing. Second part tends to be 0 when M is increasing and M tends to infinity. And then comment on this forbidden reason. What is this? So we can just see these things directly from here. Means if M is decreasing, then we can see that this whole term is increasing. Means this band turn out to be going for the up. This is going up. So we see that when M is decreasing, this frequency of the optical region, minimum frequency, will increase. Okay. So and we can see that what if M tends to 0, M tends to 0, then we will see that this M will be 0, and this whole term will tends to infinity, and this will also tends to infinity. So we'll see that this optical branch will be disappeared from the graph, and we will get just this type of curve. And this is guys, we have seen that this is nothing but the monoatomic lattice vibrations graph, which came out to be this, like this, like this, like this. So we'll get the monoatomic graph there if M tends to 0. Okay, and if M decreasing, then we will see that this is increasing, means the forbidden gap is increasing. Second point was when M is increasing, and M tends to infinity. So let me show you this from here. We have this different cases, maybe question can be asked, so let me discuss all the cases with you. What happens when m equal to m? When m equal to m, then we know that the frequencies are 2 beta by capital M, 2 beta by small m. So both will came out to be at the same place because m is m. So we'll get this type of curve, and here it was 2 beta 1 by m plus 1 by m, so it will turn out to be 4 beta by m, this frequency maximum for the optical branch, and this will be 0. So the range for optical branch in this case will be 2 beta by m to 4 beta by m optical branch, and 0 to 2 beta by small m for the acoustical branch. Then there is this case when m increases. When m increasing, then 2 beta by m will decrease, and 2 beta by m is nothing but, let me just show you this. So when m increases, this whole term decreases, so it will go down. Just like m was decreasing, then this is small m was decreasing, this is going up. If this capital M increases, this will go this down. So forbidden gap will definitely increase. So this will decrease. And what if when m tends to infinity? When this m tends to infinity, then this turn out to be 0, and this we will get a flat curve. This curve will be flatted, and at the same time we will get this type of curve, this type of curve. And when m tends to infinity, when capital M tends to infinity, see this term turn out to be 0, this term will be turn out to be 0. We will get 2 beta by m, and here also we have 2 beta by m, so this curve also flat. So at m tends to infinity, we will get both the curves are flat. So this type of curve we will get. So just remember these question can be asked from these graphs. Okay, so what happens when m tends to infinity or m increases? Okay, so let's just see the third thing, means the effect of capital M and M on the forbidden gap. So what is forbidden gap actually? So this gap is nothing but it is a region where the frequencies lying between these regions are not allowed. Means particle can't vibrate at those at these frequencies which are lying between this region, these frequencies can't be allowed. So that's why we call it the forbidden region. And the width of this region is depending on the ratio of capital M by small m. Capital M by small m. Let's see. If m decreases, optical branch shift upward. M tends to 0, optical branch disappear, as we already discussed. Not allowed frequency is what? This frequency and this frequency. The frequency lying between those frequency, root 2 beta by m, root 2 beta by small m. This frequency between them are not allowed. So this is the forbidden region. Width of forbidden band depends upon the ratio of two masses, that is capital M by m. And let's call it a constant k. When this ratio increases, forbidden gap increases. How? Capital M by m increases, means m should be increasing, m and small m should be decreasing. So when small m decreasing, this will go up. When m increasing, capital M, this will go down. So region will be increasing. And likewise, if they are decreasing, then this gap will be decreasing. Okay. Now there is one more conclusion we can take out, that smallest wavelength possible for the first brilliant zone. We will study brilliant zone in the next sections. So smallest wavelength will be possible for at k equal to pi by 2a. Okay, and this is nothing but boundary of first brilliant zone. And we can just compare. If we need to find the wavelength, then pi by 2a will be equal to 2 pi by lambda, that is k equal to 2 pi by lambda. So from here we can find that lambda equal to 4a. This is the smallest wavelength possible. Okay, so I hope these questions are clear to you. If you still have some doubts, you can ask in the comment section, or you can join the Telegram channel and the group. You can ask there. So let's move forward. Today we will study the modes of vibrations. Modes of vibrations. So there are some terms. Let me introduce you first. If I call LA, that will be longitudinal acoustic. If I call TA, that will be transverse acoustic. LO, longitudinal optical. TO, transverse optical. Okay. Now, I hope you guys know that what is longitudinal and transverse. If you don't, let me revise you. First thing, longitudinal is nothing but when particles oscillate in the direction of the motion of wave, and transverse when particles oscillate perpendicular to the direction of motion of wave. Okay, so hope you get it. So let's discuss first the 1D cases. For the one dimension cases we have acoustical mode, how they act. So the basic thing we just found from the in the previous lecture, that for the acoustical mode, particles will be oscillating in the same directions, and in the optical branch they will be oscillating in the opposite directions. Mean for the diatomic we are talking that the mutual, or the we are just saying that for the adjacent particles, means if they are these two particles, they will be moving in the same direction, and for the optical branch, these adjacent atoms will be moving in the opposite direction. Okay, so let's see, acoustical branch is nothing but about the sound wave. So we already seen that how sound wave moves. So half particles are going this side and half particles are going this side, so they are having a compression, and we know that wave moves with a means rarefaction and the compression. That's how we have the motion. So first they compress, then they rarefact. So this is 1D motion, means one dimension we have taken. These are moving this, these are moving this. Each have different amplitude. Some particle will have the maximum amplitude and some have the minimum amplitude, and here it is the zero amplitude. Then it is increasing in the opposite side. So we can represent this 1D acoustical mode in this waveform. Like this is this, and that maximum particle oscillating will be this. Means this wave is just representing this motion. This motion. Okay, and this point is representing this point, then they are in this direction, that's why amplitude in the this direction. So this wave is representing this motion, acoustical mode. So in 1D only this one mode is possible, this one mode is possible, no other mode is possible. If you are still having confusion, just search acoustical mode 1D on the Google, you will see a better picture, so we will get a good understanding. So I will suggest you to watch that, so that you can see that how they are moving. Okay. Well, I have given you already the idea. If you are good at it, you will understand. Have a good imagination. So now the 1D motion in the optical mode. We know the optical mode, the adjacent atoms will be moving in opposite directions. So this will be moving in this direction, this will be moving in this directions. Okay, this is this, this is this, this is this, this is this. So we have taken more particles. This. So this is diatomic. Okay, that's why I have taken this is capital M, this is small m. So if we represent this motion in wave, how we will represent? So we know that both are moving opposite direction. So if amplitude is plus for this, then minus for this. So we can see that for small m, that will be this type of motion, and for the capital M, this will be this type of motion. Okay, so for these only, for this optical mode in 1D, this is also only one mode is possible for the optical mode in 1D. Okay, means longitudinal mode is only possible here because they are in longitudinal waves. No transverse is possible because transverse came in 2D motion. So only one dimension longitudinal optical is possible here, and longitudinal acoustical possible is here. So one mode is possible. So please, I suggest again to watch or see a image of oscillating optical mode, these particles on the Google, and see this wave. So you will get a good understanding. Now what we find that in 1D case, longitudinal acoustical only one mode is possible, and longitudinal optical only one mode is possible. There is no transfer motion possible in one dimension, you know that. In 2D what happens, just like this is one line, add one more line here, add one more line here, then all particles are moving this way. This is like this, sound wave how they move. Now they also moving the same way as they are moving. Okay, so in 2D also there is only one mode is possible for the longitudinal acoustic. This is this like they are moving this way. More, add one more row or 3-4 rows, then they will also be moving in the same way. That's why only one mode is possible for the longitudinal acoustical in 2D also. Okay, and transverse acoustical only one mode. That will be, you have seen the water waves, they are flowing like this, all particles are going up, then down, then down, then down. So that is the mode possible, that is transverse acoustical. So that's why we written 2D 1, and longitudinal optical is 1, and it's just the same way. This is one row, Add one more row, they will be moving in the same way. That's why we have one mode possible for the two dimension also. Okay, and transverse is also one, means the way in the acoustical they will be like this is going up, this is going down, and there is only one mode possible for them also. Okay, so 2D we have transverse also, but only one mode possible. But in 3D, let's say in 3D the longitudinal acoustical means now they are more rows and they are on the upside also, they will be moving in the same way. That's why in the longitudinal acoustic we will have only one mode in 3D also. Okay, that's why longitudinal acoustic is 1, and transverse acoustical is 2. How? So first it was moving like this. In transverse the motion will be like this, particles motion, this type of motion will be there. So they can also moving like this, as you have seen in the electromagnetic waves, the B and E fields. So you imagine that way, means the this way and this way. So that's why two modes are possible for the transverse acoustical. And similarly for the longitudinal acoustical there is one mode possible only, whether it is in 3D or 2D or 1D. And for transverse optical there will be two modes, the upper side and the this side. Okay, so I hope these numbers are clear to you. Now if these numbers are clear to you, then I will give you some general formulas and the questions asked here from this area. How the questions are asked, let me tell you. If p number of particles are there in the unit cell, in a unit cell there are p number of particles, then how you find the degree of freedom? That is nothing but 3 into p. Means for one particle we know that only 3 degree of freedoms are possible on the xyz direction translational motion. So that's how we calculate the degree of freedom. For two particles that will be 3 into 2 6, for three particles 3 into 3 9. That's how. So as we are studying the diatomic crystal, so let's say total degree of freedom will be 3p, 3 into 2 6. Now acoustical degree of freedom will be 3. This number will always be 3. Just remember this. In the acoustical mode, this number will always be 3. And LA, longitudinal acoustical, will be 1. TA will be 2. This number will be fixed in all the cases. Now the remaining one will be 3p minus this FA, that will be 3. So 3p minus 3, how much remaining? 3p 6 minus 3, 3 will be remaining. So 3 will be distributed in optical degree of freedom. That will be LO1 TO2. This is nothing but transverse optical and longitudinal optical. So TO will always be twice LO. Twice LO. Just remember this. Just remember this. So now we take some examples, so you will get idea of this. If p equal to 3, total degree of freedom 9, FA will always 3, then remaining will be 6. So this is for FA will be 1 2. This is same in all cases. Now for FO, this will be 6, 3p minus 3, 9 minus 3, that will be 6. Now 6, how we divide 6 here? That will be TO equal to twice LO. Twice LO. So how we'll say here that 6 will be 3 LO and wait. So for this case LO will be 2 and TO will be 4. So TO will be twice LO here. Okay, so LO will be 2, TO will be 4. So you can see that TO is twice this LO. So I just find it from the formula, which is TO will be twice LO. So just remember this formula will be applicable everywhere. So for general formula, if we say degree of freedom, this 3p formula work on only in the 3D cases. So 3D degree of freedom will be 3p, then apply the same thing. FA will always remain 3 and LA1 TA2. FO will be 3p minus 3 and then LO p minus 1 and TO will be twice this number. In 2D cases, total degree of freedom will be 2p and FA equal to 2, LA1 TA1. Okay, in 1D cases f equal to p, p is nothing but number of particles and f is degree of freedom. So fa will be 1, La1, and in 1D there is no transverse motion possible. That's why we have Ta equal to 0, and p equal to in 1D dimension only p equal to 2 possible. Particles more than 2 are not possible in the 2 dimension, so in 1 dimension. And Fo optical is nothing but p minus 1, so that will be equal to Lo, because no transverse is possible here. Okay, so just remember these formulas. These will be very helpful for you to solve the questions directly. Okay, that will be very easy to you and very efficient way. So let's study something more. In solids we study the phonon concept. Phonons are nothing but quanta of elastic wave is called phonons. So I already told you about phonon in the previous lectures, so let's see it again. In elastic waves inside a solid, when those waves which carry energy, so that quanta of energy of wave is called the phonon. Energy of one phonon is nothing but h cut omega. Here omega is the angular frequency of the oscillations of atom in solid, and h is Planck's constant. H cut is h by 2 pi. So energy of elastic wave means if there are n phonons, then it will be n h cut omega total energy. And phonons are nothing but bosons. Bosons we know, for bosons and fermions. What are those? The difference is fermions are fractional spin. Fermions have fractional spins. Bosons have integer spin. Okay, that's the difference. The phonons are nothing but bosons. Phonons can exist only inside the solid in two way only. That is in the either in acoustical mode or in the optical mode. We already studied that they will be either in acoustical mode or in optical mode. And phonons also called quasi-particles. Quasi-particles means, what are quasi-particles? These are those particles which exist but can't be detected. Can't be detected, like electrons, protons, neutrons. We can detect those particles. Those are nothing but fundamental particles. But quasi-particles are those which can't be detectable. So phonons are quasi-particles. And for example, photons are fundamental particles which can be detected. Now we have acoustical phonons. Coherent movements. What are acoustical phonons? Where there is coherent movement of atoms uh, out of their equilibrium position, means all the particles are moving in the adjacent particles are moving or the oscillating in the same direction. That's how we have acoustical phonons. In optical phonons, out of phase movement, the adjacent particles are moving in opposite direction. That's how we have optical phonon. Now there is one more thing, that is crystal momentum. By analogy to photons and matter waves, as we have seen for the photon and matter waves, there is a momentum and pressure exists on our skin and everything in the world. We can see the pressure applied by the sun rays. That's how we determine their momentum for the matter waves. So by the analogy, we can also find this for the phonons. Phonons have been treated with wave vector, that is k, as though it has a momentum h cut k. So we just put the momentum of phonon according to the analogy with photon and matter waves, that is h cut omega. However, this is not strictly correct, because h cut k is not actually a physical momentum. It is called the crystal momentum. This is nothing but crystal momentum. This is because k is only determined up to addition of constant vectors, the reciprocal lattice vectors. We will study the lattice vectors and all. So I will told you that at that time. So what the study of phonons help us? Where it helps us? So it helps us in the understanding of thermal conductivity of the solids for the better understanding, and the specific heat of solids, optical properties of solids. So all properties are affected by the phonons. So that's why we study phonons. Okay. So let's end today's lecture here. Tomorrow we will study about the specific heats of solid. So how they are actually works, means we will go in detail. Okay. Till then, thank you.